if we had a half spherical face on a container and then allowed the material to go on forever, like a trough full of water with half a Petri dish here and sealed so the water won't leak out, then our parallel rays would indeed focus at some point. And by the geometry of the situation, if we know the index of refraction of this material and the index of refraction of this material, we can easily do a little geometry and determine where the focal point will lie. And we'll see some of that geometry shortly. For a real, well, for an actual circular lens, like your soft drink bottle or whatever, the Petri dish, what really happens now is that the parallel rays come in for the from where the index of refraction is in air, which is very close to 1, gets refracted toward the normal. Remember, the normal line is just a radial line for this circle. Hits the other face, and instead of going straight through and focusing like right about here, gets bent back slightly and focuses out here a little bit. Okay? And this parallel ray will come through and get bent back and focus at the same point. The ray through the middle goes undisturbed and of course meets also at the same point. This distance from the edge of the circular lens to the point of focus should be approximately 1/2 r for water. The actual distance turns out to be 2 minus n over 2n minus 2 quantity times r. And you see that if n is 1.33 or about 1 1/3, then 2 minus n is 2/3. 2n would be 2 2/3. 2 2/3 minus 2 is 2/3. So we'd have 2/3 over 2/3 times r, which is just r. And I said this was 1/2 r. I meant it's 1/2 the diameter. So let me just cross out that 1/2. It's not really 1/2 r, it's r. Okay? So this distance here is approximately equal to the radius r. If you have a material with a very high index of refraction, now n equals 2 is a very high index, and the n equals 2 of course applies inside the lens. N equals 1 in air, approximately 1. In that case, 2 minus n, well, if n is 2, 2 minus n is 0. So 2 minus n over 2n minus 2 is 0, so that the distance beyond the end of the lens at which this thing focuses is 0. And we see that we have focus at this point, so that all the rays would focus right at the very edge of the lens. Now, let me back up. When I say all the rays, I mean all the rays close to the center of the lens. Actually, the rays that hit way out here don't focus in the same point. And these rays don't actually focus in exactly the same point, but as long as this distance here is small compared to the radius, then they focus very nearly at the same point. In the case where the index of refraction is greater than 2, this formula doesn't necessarily apply. If you wish, you can work out the details and see whether it does or not. Parallel rays come in and they converge at a point inside the lens. Now actually, I don't know of any material that would have the rays converging quite this far back from the end of the lens. The highest index of refraction that I know off the top of my head is that of diamond, which is around 2.5 or something. And I don't think 2.5 would give you a focus this close to the center. Could be wrong. I haven't worked that one out. But that's, if you recall on the video clip, when I got a focus that was in around this range by accidentally misdrawing my lines, and that was a real accident. I didn't just pretend to do that to make a point. I was pretty well shocked because I didn't know of anything that would focus in that close other than diamond, and I really didn't think that the scientific company had accidentally supplied us with diamond circular lenses. Didn't have the right weight anyhow. It sure felt like acrylic, didn't act like diamond in any other way. Although I did take it down to my jeweler's and check it out.